Welcome everyone to the Colchin seminar today. It's my great pleasure to introduce Bertrand Teguia, who will today talk about D-algebraic sequences.
Thank you. Thank you for the introduction, and thank you to the organizers for the invitation. So we're going to discuss this object where the D on the title is for different sequence. Okay, we will start with a motivating example, which I call a toy example here. We consider the sequence Sn. This is a sequence obtained by the arctangent functions. It is the Leibniz formula for pi, and this it's known to converge to pi over 4. So we are going to try to accelerate the rate of convergence of this sequence to pi over 4. And okay, it is known that this is one of the slowest sequence converging to pi also. And the technique we are going to consider is the so-called Atkins delta square process to a given sequence Sn. The delta square process will associate the sequence of term Tn, where Tn is obtained by this nonlinear rational expression, as you can see in Formula 2. And it is known that in general, Tn will converge faster to the limit of the original sequence. So now, let's have a look at the sequence Sn, closer look. Okay, what is happening? Yeah. So we consider the summand of this sequence. The summand is polynomial. By that, I mean that the summand satisfies a linear recursion with polynomial coefficient in the index variable here, which is k. And when it's holonomic, using a non-result from last year, we know that it is always possible to compute a rational recursion from the holonomic equations. So it is easy to compute the holonomic equation from the summand. This summand AK, you just compute the ratio of two consecutive times, you have a rational function. You have the first order reconciliation. And from that reconciliation, you can deduce this equation here, number 3. It's a rational recursive relation. And the result of this paper, jointly with James Burrell, says that if you are given a linear recurrence relation with polynomial coefficients, so if you call the degree, let's say D, the maximum degree of the polynomial coefficient, and the order R, then you're always able to compute a rational recursive relation like this one, where the order will be R plus D. A quite nice result, I would say. Okay, then we apply this, we obtain this rational recursion. Now what we want is a recursive formula for our original sequence here, Sn. And this is possible from the recursion number 4. And this is what we obtain here. This is one of the closure properties that you will see for D-algebraic sequences. But already this is one of the simplest, because if you have a recursive formula like this one, it's possible to deduce such a relation for a partial sum using some substitution. So now the next thing we are going to see to do is to compute the Atkins sequences, the Atkins sequence associated to our sequence Sn. And to do that, we use a software. The software here is D-algebraic. D-algebraic is a sub-package of the package NLDE. The slide will be available. You can click on this link to go to the web page of the package. And the NLD is for nonlinear algebra and difference and differential equations. So D-algebraic is a sub-package dedicated to operations with the algebraic sequences. And here what it does is it uses the command unary D-algebraic sec. The recursion RE is the recursive relation for the sequence. Here our sequence, the unknown variable is Sn. And we want a recursion for this transformation of the sequence. So let's do that in a Maple worksheet. Can you see? I hope you can see the Maple worksheet. So we start the worksheet, we load the sub-package, the algebraic. We are in the introduction of the presentation. This, we already saw it. This is the recursion for the summand. This is the partial sum, the recursion that we saw on the slide. And now we use D-algebraic to compute an algebraic difference equation for this transformation of the sequence Sn. If you try to compute it after a few seconds, you get the result. This is what we obtain here. Now, in order to compute or to launch, let's say the sequence, you need 3 terms because this is a recursive relation of order 3. So in order to launch it, you need 3 terms, and to compute those 3 terms, we will need 5 terms or 4 terms of the original sequence. The original sequence can be computed with this small code here. This is a small code to compute the partial sum of -1 to the k over 2k plus 1. So I just have this code. I will use edken to compute the first few terms of the sequence Tn. So this is just the same transformation here. And then this command here will compute the first 3 terms of the sequence Tn. This is what we do. We obtain these numbers, and now we evaluate what we want to. So we are going to compute the 4th term of the sequence Tn. This is supposed to get closer to the value of pi/4 than the original sequence. So we do it here. What we obtain from this equation, we substitute these values, the values T0, T1, T2, in this equation for Tn, Tn plus 1, Tn plus 2. And in order to compute now, we do this here, we obtain a quadratic equation for Tn plus 3. N plus 3 here should be, you replace 0, by, n by 0 is the 4th term of the sequence. The advantage of this kind of equation is that you don't necessarily need to substitute the index variable, since it does not appear as in the coefficient of the equation. And if you solve this quadratic equation, you have 2 values. This is expected because the Aitken transformation only does rational transformation. So you expect that whatever the equation that you have here, there should be irrational numbers as a root of the equation. And these 2 values approximate pi/4 better than the 10 first value of the original sequence, as you can see here. This is pi/4 approximation for the, let's say, this number of decimals after the comma. And here, these are these 2 values approximate pi/4 greater than the value given by the original sequence up to the 10th term of the sequence, as you can see in this. And this can be done for many sequences. So this is how I wanted to introduce my talk. And now I'm going to define the object behind such computations. And so the advantage with the Aitken transformation is that when you do such transformation for a D-algebraic sequence, you are supposed to get always a D-algebraic sequence. So you are working with an object that is unchanged by such transformations. So in order to define this, we will first give the setting, the usual setting. We consider a difference field of characteristic 0. Here, sigma is an endomorphism in K. And we consider the ring of difference polynomials in this of a difference indeterminate X. So this is the ring, and sigma here is defined like this one. Now, a difference polynomial P is said to be in normal form when X effectively occurs. So the minimal shift in the equation in the difference polynomials is 0, the minimal order, let's say. And the order is defined as the order when this X occurs in the equation. So it's denoted order. P is the maximum J, so that sigma J effectively occurs in P when P is written as a normal form. So you always have X and the maximum J. So the degree now is the total degree of a difference polynomial is the total degree when it's seen as a multivariate polynomials with order P plus 1 variables, starting from X to the order. And it says to be linear in its Higher-Shift term when the term of order P appears with degree 1. So the equation P equals 0 is what we call algebraic difference equation. Now, just to give an example, this P here is the the equation, the difference polynomial for the Fibonacci sequence, sigma square minus sigma x minus 1. The order is 2, the degree is 1. Here we have another one. This is q, but here we have sigma x as the minimal order. So we need to shift it back. So this will be like sigma x minus x squared, and the order is 1. The degree is 2 because of the 2 here. Now, in classical algebraic geometry, when you have a multivariate polynomial, the zeros are seen as point in affine n space for some n. And now what we are considering are zeros of different polynomials. You could say these are vanishing point S that annihilates all transformation of the difference polynomial for J in the ranging to the integers. So clearly, S here is a sequence, but not all sequence satisfy such polynomials, such equations, and we can find examples. And here, the example I have in mind is this one, n to the n is a sequence that does not satisfy an algebraic difference equations. So in the paper, the preprint accompanying this presentation, we just decided to call it K Aleph 0, where Aleph 0 is just the cardinality of the set of integers. So just to put a difference between the difference ring that we will consider where we will look at solutions of difference equations, and the entire difference ring of sequences. So now, just to give an example of these zeros of difference polynomial, consider the difference ring where sigma is the automorphism which transform every complex number to its conjugate, here a to a bar, and you have this difference polynomial x squared plus 1. So in standard difference algebra, you can see two solutions to this in this difference ring. For this difference ring, those will be R transformation of I and R transformation of minus I, where I is the imaginary unit. But there are other solutions, and the computations with this equation will consider all these solutions. For instance, this guy here, I minus I minus I minus I minus I, is also a solution. So this is just to show you why sometimes it's not even necessary to know what sigma is exactly, but finding some solutions, and depending on the solution that you are interested in, you can now try to define the endomorphism or automorphism that you will need to move to the coordinates of these solutions. So this is why I put here the coordinate view to say a kind of affine the algebraic sequences. Now, in order to define, so a priori, we are supposing already that KLF0 sigma prime is a kind of difference ring, but we will see from the closure properties later that this is indeed a difference ring. So consider P is to define the zero. Consider P in the ring of difference polynomials and the sequence Sn in this difference ring. And we say that this sequence is a zero of P if under the unique homomorphism of difference rings that send X to that sequence, the difference polynomials is sent to 0. And now, according also to the previous examples, one may ask if it is always possible to have a 0, because depending on the automorphism or endomorphism, you may not even know if a solutions of the difference polynomial a 0 exists at all. And this is given already in the 1948 by Kohn, who says that every non-constant difference polynomial has a 0. And from that, we can define safely, let's say, a D-algebraic sequence as a 0 of a non-constant difference polynomial over K. But these zeros, I will say, they are quite weird, as we will see from some examples that you can have two different polynomials where zeros where terms of the terms of the sequence are shared by two different polynomials, and both define the sequence. So it's like a factorization, but the zeros are just changing the polynomials at each index. Now, difference algebraic closure properties. So now that we have a definition, we can also associate or seize a ring of difference polynomials as this difference ring here, where Sn will denote as zeros of the difference polynomial P in this difference ring. So the variable x will be replaced directly by a symbolic term of the sequence. So you can see the sequence in the equation directly. So this is how this is what we will use, and it's a common notation. And then what we are going to do now is to consider rational expression of the algebraic sequences. So here we have S1 up to S capital N. They are the algebraic sequences. And we consider f a rational function. And a rational function of these the algebraic sequences. We want to find an algebraic difference equation or a difference polynomials that vanish at all at this expression of the algebraic sequence. Yes. So the idea is quite simple. We want to construct a kind of dynamical system, and we tell it's the first order equation where the right hand side will be a rational function. So we do this transformation here because we create new variable for all the SI. We have wj plus 1 equal to s1 n plus j. So we are just creating new variable associated to each difference polynomial and their differential difference in determinants. So when you do this, you can now, for every w, you are able to compute the shift using all the created difference indeterminates. Since we have, from this relation here, we know how to compute the next term of Si for any I. And using the difference equation, you know how to also, yes, to compute the term of the highest order shift. So this one, and we see the difference polynomial as this, where mj is the degree of the highest order term, so the term of the order, and w is already replacing the variable si immediately. This is, I think one can even use the slide, what the notations here is a kind of, we are already building a kind of algorithm so that if you implement this, you're going to get exactly the computation, so the implementation in NLTE. So this is the coefficient, often called initial, which will also be helpful for the dynamical system. So, and this is what we obtain after doing this change of variables and writing all the polynomials. You obtain something which looks like this. And we have the mu here. They are degrees, usually representing the degree of the highest order shift. Here, mu1 up to mu m, representing the mj that you see in equation 10 here. And usually the mu I, as you can see, some rational dynamical system or polynomial dynamical system, these are usually 1. And we know how to eliminate some variables when you have such a system. But when you have the mu, actually the good thing is that the technique still applies. The only thing is that now for the saturation, you only use the the coefficient of the highest order shift with the degree. So we use this to saturate the corresponding ideals, and you're able to do the elimination because you still have this structure of a triangular set. And yeah, this is how we consider this ideal, and the saturation will be done with Q, where Q here is the H, but Q here is the common denominator from the system. So when you have the system here, this right-hand side of the system, they are rational expression, and we have denominators in every equation. And this is called Q, and you consider all the shift of that Q. And so IMF will be truncated when in the theorem. So this is what the theorem says. There is M here represent all the variables that you created while building the system. And this is always going to give you a non-trivial elimination ideal. And yeah, this is basically how the closure properties are implemented. Just to give you some of the closure properties that can be achieved by this transformation, you have addition, you have multiplication, you also have order bound. If you have a difference equation, order R1, another of order R2, then you can build a difference equation of order R1 plus R2 for the sum or the product, and also have this. So multiplication, division, taking radicals, partial product, partial sum. And in this relation, you're also allowed to introduce shift. Just to say, okay, for instance, if you consider addition here, you can also have the closure property un plus k vn plus j, where j should be less than the order of the equation for v, and k should be less than the order of the equation for u. This is, for instance, what we did for the Atkins sequence when we computed. If you see, we had an equation of order 3, but the transformation that we were requesting was a transformation of order 2. So everything was fine for the computation. And one closure properties on order closure property, which I think I will not discuss today, but maybe the next presentation to this in this topic, is the closure property related to the subsequence at arithmetic progression. So if you have a D-algebraic sequence, then every subsequence, the subsequence SDN is also D-algebraic, and the order is also R, but in a difference ring, or difference polynomials. This one, sigma B, is a kind of jump. So you have to define the new operator, and you can build, again, a dynamical system, radical rational like previously, and you can compute a difference equation satisfied by the subsequence. The construction of this system is like a certificate attesting that the equation actually exists. In the paper, one example was given with the Catalan sequence. Before this, I just want to compute one example. This is a sequence. You know that this you can try. This does not satisfy the linear recurrence relation. But you know that factorial n satisfies a linear recurrence relation, which is this one. Quite simple. an plus 1 is n plus 1 an. So you can use holonomic to simple rhetoric. This is the conversion of a holonomic equation to a rational recursive sequence. So you can compute this equation here. And you know that this is also valid for factorial. But from there now you can find the equation for S by using the closure property of a rational function of an. So you have 1 over 1 plus a. You ask the code to compute an equation for S, where S is 1 over 1 plus a. And you get this. This is a difference equation of order 2 and degree 4. And as you can see, it is also linear in its Higher shift. So you can write this recursively like this. Now I want to explore. This is not yet in any paper. It's just an exploration with guessing. Guessing is the kind of construction of an equation given the terms, in this case, the terms of the sequence. You know a few terms of the sequence, maybe up to 10 or 11 or any number. And we want to construct an equation, in this case, an algebraic difference equation for the sequence. And the idea we use is a kind of, so you have to use ansatz with bounded degrees lexicographic monomial ordering in DS. For instance, if you would say degree 2, then you will always only consider the the monomials of degree 2, but ranked in a lexicographic monomial ordering. And you repeat this process, you only have constant coefficient. So it's quite not complicated to implement. And this was also done. A similar implementation was done by Hebich, Valdemar, and Rubé Martin. I think this was done in Mathematica, so I couldn't really try for now. I don't know. I didn't have access. So I implemented something just to still continuing the exploration of these the algebraic sequences. And just to show you one example, yeah, just to start, let's start with this sequence. These are even indexed primes. I don't mean to say this is satisfied by the sequence. It's just that the guess is quite interesting. This is not completely meaningless because we have an equation here with some 1, 2, 3, yeah, 4, 5 factors. And you can use this to generate up to 54 terms of this sequence of prime numbers. The reason is at any index, you have one of these zeros of the equation is a term of that sequence. So in order to produce the sequence, you just need to know which automorphism in the difference ring can be used to go from one term to its next term at each point. This is to be defined, but at least we know already using the guessing algorithm that such an equation can be used to generate up to 44 terms of that sequence. And one thing I want to mention also is that these 12, 6, 8, 10, these are prime gaps, well-known prime gaps, as you can, and like the 6 and the 12. And it also tells you that if you want to find an algebraic difference equations for the primes, here is an idea of how to do it. So you will use prime gaps, and there will be maybe another polynomials which will be used to compute the next term when the prime gaps does not apply. For instance, in this sequence here, the term 7 is a solution of this cubic equation in the guess. And yeah, this is all I wanted to say about these examples. Another examples I want to show is, yeah, it comes back to our initial converging partial sums. This was the summand. So I defined this sequence and I computed the 21 first terms of the sequence. These are the 21 first terms. And I want to guess the guess always, when the guess succeeds, the equation you obtain may always mean something because internally you have you obtain a linear system that is overdetermined in general. And so if it has a solution, it might mean something to the sequence. So here, what I asked the algorithm to do is to look for an algebraic difference equation of degree 4 for this sequence here. And we know already that this sequence has this rational recursion. We know how we obtained this already. But now I want to look for something else. And when we do the computation, did I launch it? Yeah, okay, we obtain this. And this can be factorized in two. So we have two terms, we have two equations. And so you have two expressions for the next term. So it's a first order equation, but we have two equations. And this tells you two ways of obtaining the next term of the sequence. If you use one of the equation as an equation to generate the terms of this sequence, you will not be able to generate all the terms. So in this case, you must use both. And I will show you, these are still guessing, not yet the proof. There's no proof at this point. So this is still the sequence U. These are all terms up to the 41th terms. And if you use this sequence, so we define the sequence that will use this if the index is even, and use this expression, the second one, if n is odd. And if you use this, you generate the sequence. So the two sequence has, I think it can be proven, the two sequence are the same, but we found a different expression of the same sequence by asking a D-algebraic equation of degree 4. So and you can continue like this up to 1,000 times. You will see that the difference is 0, meaning that both sequence agrees on all these terms. So so one question, maybe I will leave this, I will end my talk with the question, is that is it possible, maybe this is known to the audience, so is it possible to start from this recursion here and know that there is it looks like a factorization, but there is there are first order equation for the same the algebraic sequence, but with first order terms. But where here to compute the next terms, you use two different equations that are obtained like this. So I hope I told this how it's in the correct way. So okay, the question is, can this one? So it's a kind of it looks like we change even um, the shift. So because here we are in this expression here we are shifting plus one, but here it looks like we are doing something in the shift plus two because the expression the expression of the sequence is it tells you how to compute the term given. Yeah, so you use a2n with a2n minus 1, and then you use a2n plus 1 with a2n. And this was guessed. This was obtained from the terms of the sequence. And I found this interesting. And yeah, this is how I wanted to finish my talk. And yeah, I'm on time. Thank you very much.
Thank you very much, Bertrand, for this very interesting talk. Now we are ready for questions and remarks. Please just unmute yourself or write in the chat. Maybe I can start with a quick question. When you refer to the method of guessing, what would be a good reference? Is this in your work, or are there other references?
Yeah, I think also even the Manuel Kawas, in his book, for instance,
Okay, I see. Now,
yeah, I think the first chapter is about guessing. They have powerful guessing approach, I think. But this is still even naive because they do more things with the guessing, like guessing with small data. But the methodology is the same.
yeah, thank you.
Hello, thanks for the talk. I was wondering, you mentioned that you don't have Mathematica, is that correct?
I can have access to it, but the thing is, I did not try the package because I need to. I'm not really familiar with Mathematica, so I will need some time. But I can have access to Mathematica at the university.
Oh, okay, all right.
Yeah.
So who are the people who implemented the thing in Mathematica?
These two guys, the two guys here. So they have a guessing algorithm similar to this one, and they consider in the guessing they have non-constant coefficients. So the index variable can appear, and I guess it will be more difficult.
Is there any estimate of how fast or some measure of how fast these processes compute convergence?
which one do you mean the
And let's say
guessing?
just, I mean, even for the original, what, the icon process?
Ah, the Etkin.
Yeah,
Oh, how fast is it you mean?
right. I mean, is there any estimate of how fast in general? I mean, you gave an example, right?
Yes. I don't really know. Uh, I don't know. I'm not. I don't want to say something wrong, anything. But so because but from what I read, from what I remember, is that when you have a rate of convergence which is maybe quadratic, then using Etkin will generally improve that convergence. So it could become something almost linear. I'm not sure, but I just want to mention.
Can also that process be repeated,
Sorry,
iterated? I mean, can it be iterated, that process?
the process. Yeah, for instance, at the introduction, from what I gave here, uh, in this example, now that we have all terms, so if we have with these three terms, you can compute all terms of the sequence of the Atkins sequence for Sn. And you to compute the next terms, you will always use this equation here. It will always give you a quadratic equation. You solve it. All roots are approximation of the limit. You repeat this process. Yeah, it's a recursive computation. But here, what the advantage of using this closure property of the algebraic sequences is that it allows you to have directly an equation for Tn. So you don't need Sn as soon as you have the necessary initial values. You can just do the computation directly with the sequence. And this could be like a method to even find good rational approximations to some known constant. Because with this, as the Aitken transformation will give you another sequence that will convert, and all those will be rational numbers. So you will get rational and rational numbers. Sometimes the rational numbers can have not many digits, I would say, and then be best approximation to the limit.
Okay. Thank you.
Any further questions? You had this example where you mentioned prime gaps. I somehow missed it. Was it on the slide maybe? Or
This
maybe
slide.
in
Prime guess. Yes.
yeah. So I must say I didn't quite get where do you have the prime gap here?
The prime gaps are this one: 10, 8, 6, 12. So it's saying the equation is saying, okay, well, when you have a prime, either you add 6, you add 8, you add 10, or you add 12 to get the next prime in this sequence, or you solve this cubic equation. And yeah, and you are able for this sequence, you're able to do this for up to 44 times. You always
and
being able to.
afterwards?
Afterwards, I think after the 55 terms give a prime which is not in this sequence. It give a prime in the odd index primes. This is not what, yes. So this is where it fails.
Yeah, I somehow missed that. Okay, thank you very much for the clarification. Are there further questions? Nothing in the chat. That doesn't seem to be the case. So we thank. Yeah, please.
Yeah, I'm interested in this even index primes. Where do they come from? I mean, in what context does people want to study this sequence?
Oh, I can't say because we have the OEIS, the Online Encyclopedia of Integer Sequences. So when you have some algorithm you want to try on some good examples, and this was to me one of the goods. Like, just try. But yeah, apparently some people study these.
So what was this other, besides the 6, 8, 10, and 12, which of course can come from the beginning of the sequence, satisfied by that. Have you solved the degree 8 equation?
Yeah, when for instance, if you start this with 3,
Right.
so 7 is not 3 plus 10, neither 3 plus 8, neither 3 plus 6, neither 3 plus 12. So you will have to solve the last equation for 7. And if you put 3 for Sn in that equation, 7 will be one of the root.
Uh-huh. I see.
But these equations, they are sharing primes. When you know the previous prime, they share the next prime. So one of them will have the next term, and this
Right.
will be repeated.
But do we know? So, for example, 13 to 19, the difference is 6.
Yes, so it will be that one.
Right. But do we know how many prime pairs have different 6? I mean, from
Do we know?
yeah.
They could be, I don't know. But I guess there should be infinite many.
I mean that's really the prime gap, right? I mean,
Yeah, 6 and 12 are quite 6 and 12. I think they are popular prime gaps. Even in the polymath projects, you will see some works about 6 and 12 as gaps.
I see. No.
Are there further
Oh,
questions?
it's not quite.
Yeah.
Sorry.
Yeah,
It's
sure.
not quite prime gaps because you're only talking about even index primes. So it's a little jump.
Yeah, but these gaps appears even for non-even, not the odd prime gaps. I think this is valid for many primes, and this is why I said you can continue this sequence if you're interested in all primes and you start this way.
Right.
After the 54 terms, and if you want just to get primes in your sequence, then you can go even up to, I think I tried this, you can go up to 80 or 84 terms.
Uh-huh.
Because you always get a prime somewhere. But at some point, when the gaps between becomes large, I think this will have the gap becomes large. I think the gap the weird gap, I think it was 80 or something. And then at that time this fails completely. I could not find the prime. So it also gives an idea of how to construct or how to show that even the sequence of primes cannot satisfy such an equation. Because if you want to build one, you will are not difference algebraic. Because if you want to build one, you will certainly consider these prime gaps and some equation like these big factors here, and you will show that at some point. One of the primes will not be solutions to the equation you have. So therefore, this cannot exist. Something like this. So it gives you an insight of the proof of the non-D-algebraicity of primes.
Okay. Oh, very interesting. Thank you.
Are there further questions? That doesn't seem to be the case. So we thank Bertrand again for this very interesting talk. Thank you very much.
Thank you.
And see you next week.